Hello everybody. So this one I think is going to take a little while, so I'm going to try and get through this as quick as possible because I'm going to have to do some fumbling around with this thing here. Alright, so as quick as possible we're going to try and cover what happens with perpendicular bisectors and angle bisectors in triangles. So we've been talking about perpendicular bisectors and angle bisectors and the unique properties. Well, what happens when we put them in the middle of a triangle and use them on the sides of our triangles? We're going to form what's called a circumcenter and an incenter, and we're going to construct these things, and they have some neat properties. So vocab today involves the word concurrent, point of concurrency, then circumcenters, what it means to be circumscribed about a polygon, and then incenters and inscribed in. So here we go. Starting again with a little vocab. Now, when three lines all meet at one point, as these three lines do, they all meet right there at one point. That point is called the point of concurrency, and the three lines are said to be concurrent. Okay, so when three lines meet, they are concurrent and they meet at a point of concurrency. That's really important for what we're about to do coming up here. So remember what we did the other day. Once again, we're going to create perpendicular bisectors by using our little arcs. One there, one here, and connecting where they intersect. Okay, so once again, we're going to create perpendicular bisectors, and we're going to do a lot of this today by doing exactly what you just saw there. Now we're going to connect the dots. Let me make it a red, blue line, blue line, blue line. Right? Create perpendicular bisectors. Okay, and then we're going to do angle bisectors again, but I forgot to put a slide there to review that. So we were doing that yesterday, so I hope that's okay. Anyway, perpendicular bisectors. What happens when we make perpendicular bisectors for all the three sides of a given triangle? So what I am about to do, as quick as possible again, is create arcs that will allow me to make get my little crosses there. And hopefully this is going to work. Dang it. That one a little bit better. Okay, make sure I'm in my place, pretty close. Alright, so a couple arcs, a couple others over here, that one right here, and finally let's make one that's a little bit larger, make a big old arc, and hopefully we'll have a point here that crosses with it. I'm mumbling to myself, I apologize. But again, trying to go quick as I can here. Alright, here we go. Now, that should allow me to make my three lines, which should all, if I did it right. Okay, one perpendicular bisector, two perpendicular bisectors, three perpendicular bisectors, and if I did it right, they will all meet at one point, proving our theory here that the perpendicular bisectors form perpendicular bisectors on all the sides of a triangle. Those perpendicular bisectors are concurrent. There we go. That's enough. Here we go. Perpendicular bisectors of the sides of a triangle are congruent. That point of concurrency of the perpendicular bisectors is called a circumcenter. What we have here is a circumcenter. All right. Cool thing about circumcenters. Alright, so this is basically having done the same thing earlier. Let me get rid of these lines, the red arcs. Don't need those anymore. We see the green bisectors forming right there. All right, now let me make sure I'm in the right place. Okay, what I have here, if I put my compass right there, look what's going to happen. Then I'm going to set my writing end of the compass to this corner right here, and look what happens. Notice how the circumcenter, when we make a perfect circle around it, actually barely kisses, barely touches each of the corners. What this means, guys, the circumcenter is equidistant from each of the angles, each of the vertexes of a triangle. So the circumcenter, the distance from here to here, is the same as the distance from here to here. If those lines were straight, you'd be really impressed. Let me try it again. Okay, let me make straight lines. Okay, so the distance in purple from the circumcenter to the corner is the same as the distance from the circumcenter to the corner is the same as that distance. Okay, the circle shows us that we're equidistant from each of the vertices of the triangle when we make a circumcenter. Okay, so the circumcenter is equally distant from each of the three corners. We can draw that perfect circle again, and again prove the point that we can make a figure like that. That circle is known as what is known as circumscribed about the triangle. So if it barely touches each of the corners of a polygon, doesn't have to be a triangle, could also be a square, pentagon, hexagon, anything, but a circle that barely encompasses each of those corners is called circumscribed about the polygon. In this case, the red circle is circumscribed about the triangle. All right? All right. Now, I know this looks busy, but it goes to prove a point. Move that out of the way. And I have basically done all the work to create the circumcenters in each of these cases. What you're going to find out as we move all the garbage out of the way as best I can, okay, you will see that for an acute triangle, as we have up here on the top left, the circumcenter will be in the middle of the circle. In the center, we have a right triangle. You will see that the circumcenter is on the triangle. And for an obtuse triangle, as we have down here on the bottom right, the circumcenter, you will notice, is outside of the triangle. Doesn't change the property, okay? Still, if we are going to use our circumcenter, it's still always going to be equidistant from the three corners. We can still make a circumscribed circle, whether the circle is, or whether the incenter is in the circle or on the circle, circumcenter, whether the circumcenter is in the circle or on the circle in the case of a right triangle. I'm a little short there, but, or whether the circumcenter is outside the triangle in the case of an obtuse triangle, yep. Yeah. We are still going to be able to make our circumscribed circles. We see the properties of the triangle. Again, a little bit off, but you guys get the message, I hope, get the point. Okay, right triangle, circumcenter is on the triangle itself. Cute. We're inside. Obtuse. We are outside. Okay. Kind of problem this does for us is that we got three friends, and they're meeting at the fair. They're a very democratic group. They want to meet at a point that's equidistant from the gates they came in at. Where should they meet? So Ron comes in north, Harry comes in at the west, Hermione comes in at the south. How should we find out where those guys are going to meet? Well, let's check it out. Let's make ourselves a triangle. And see how quickly I can do this. Oh, purple. Okay. So, using our theory that if we make a circumcenter, then we will be able to find the point that's equally distant from the three corners of a triangle. Well, here's our three corners of a triangle. Let us go ahead and make some arcs. Let's see if I do this good enough. Ooh, not quite. Okay, we'll do this one over here then. So there's one. Make this one a little bigger. There's two. And shucks. Yeah, plan B. Didn't need to do that. Let's start over with this arc here since I messed it up. Alright, hope you guys are getting the point. Now let's create our third arc over here. See what it does. Yeah, I know what it does. It's going to be too hard to draw that. But in the interest of time, we're just going to move on here. Okay, we're going to connect the dots and form the three perpendicular bisectors. Okay, one of them going here like this, right? One of them going here like this, right? And one of them that must be going here like this, right? So, I'm getting rid of all the red as much as possible. That was nice. We find that the actual best place for these guys to meet is outside the gates, but still, the point is the point that is equidistant from the three gates is right down here by the bumper cars, just outside the gates. That's where they should meet if they wanted to meet at a place that's equidistant from all three of them. All right, hope you like that. So next, remember how we did angle bisectors? Now these should be easier, I hope. Okay, remember angle bisectors. We're going to do that now. Okay, so I'm going to make three angle bisectors for this. One for each angle in the triangle. Remember how we did them? Make a little arc there. And from there, we're going to go 1, 2. Okay. And from there, I'm also going to make an arc here, which then go here. Ooh, this is going to be ugly. here. Funny, I think I'm going to hit the, okay, no, okay. And then here, make our arc, that, and go here and here. Okay, so we remembering all this? When we make angle bisectors now, lines, they're going to be green. All right, going to go right through that point right there. One of them that's going to go through that point right there. And one of them that's going to go through this right there. And get rid of all of our red. What we have now created is another point. The angle bisectors of a triangle are also concurrent. The point of concurrency for angle bisectors is known as an incenter. So the perpendicular bisectors create what's known as a circumcenter. Angle bisectors create what's known as an incenter. So since these three lines were created from angle bisectors, they converge at this point here, which is called the incenter. All right. So bisectors of angles of a triangle are concurrent. Point of concurrency is called an incenter. Here's the same picture that I had before. Let's get rid of the green. Look at the incenters. Look at the incenter. And the cool thing about the incenter is we can draw a circle there as well. Only this circle, where the circumcenter was equally distant from the three vertices, the incenter, oh, just a heck of a time with that line there. There we go. The incenter is going to be equally distant from each of the three sides. So I'm going to set my compass point right here, try to find a location as much as possible that is perpendicular, and create what is known as a inscribed circle. And if I had done it perfectly, this would barely kiss all three sides. I'm a little bit small, but there's the point. I did it better over here. So we're going to try one more time here. Okay, the incenter creates a circle that perfectly touches the three sides at one point. All right, that's called an inscribed circle. Okay, and to picture this, what you're picturing is a circle that just barely touches at one point, a point what we call a point of tangency, barely touches the triangle at one point on each of the sides. That's called an inscribed circle. All right, so kind of problem we're going to do with this. All right, if GE is 2x minus 7 and GF is x plus 4, what is GD? Well, the tick marks here are going to tell us that each of these, GB, GA, and GC, is in fact an angle bisector. And what that means is that point G is an incenter and is perfectly equidistant from each of the three sides. Since GF, GE, and GD are defined to be the distance to the sides because they are perpendicular distances, we know that all three of these sides, of these lengths, must be the same. GD, GF, and GE, their distances from G must all be equal. So we set these two equations, or these two expressions, equal to one another. We solve, we find that x is 11. We plug them in, we find out that each of these distances, this one is 15, as is this one, as is this one. All right, makes sense? I'm going to leave you from here, write a summary, and we will see you tomorrow.